Hi there, graduate students. So this is ARC2044, or Structures 1. I'm Shannon Hilchey. I'm going to be your teacher for the next 24 lectures. I am a practicing structural engineer. I have my own company called Fat Lab that does high-end, small-scale installations. So art pieces, canopies, stairs, guardrails, all the kind of fancy fun stuff. I worked for years at Blackwell Engineering. I was an associate there. And then I left that for a while to try out Cast Connects, which was, well, they still are. They're a really, really cool company doing all kinds of cast steel elements. Pretty common in Europe, but it was not common here in North America. And they kind of created this whole process that they use different foundries for, and they're from U of T. They both did their PhDs and masters here at U of T and the engineering department. And they do they have high-end engineering connections, but they also have high-end architectural connections. So really cool stuff. I started my company in 2014, and probably 5 months after I started my company, U of T asked me if I'd start teaching the structures curriculum here, an opportunity that I was just thrilled to take up. So I've been teaching that for the past 6 years, and in that time they've added the undergraduate program now has a structurals course that I also teach, and periodically I'll do an elective as well. And so this term, which I agreed to long before COVID hit, I'm doing this class, the undergraduate class, and also an elective, and also writing a book in there. And my 2-year-old and 4-year-old will be being homeschooled. So it's a pretty full term. We're going to beg each other to be nice to each other. I'll be nice to you if you're nice to me. And we'll try to get through this craziness together. Let me get up here. This is obviously the first time I've been doing the lectures this way, and the software that I'm using to kind of split the screen here, I downloaded about an hour ago. So we'll figure out cooler ways to kind of go about this as well. Last spring, when things kind of all went to pot, the only way I could do it was I plugged my computer into my TV, and then I jury-rigged my phone on this non-tripod as if it was a tripod to record the television screen and myself as I showed the lectures as if it was the old style of teaching. The one limit in this format is we'll definitely do math, and I think there's an absolutely huge benefit of you guys seeing the calculations written out. I haven't figured out quite how to do that within this kind of same video. That I should be able to do it, I just haven't had the time to tweak it. But if I never solve that, I have another plan, which is separate from this video. All of the worked out examples will be done in a separate video where it'll literally record my hand writing out all of the math while I talk through it for you guys. So you could hear the thought process behind every single number as we're going through it. Disadvantage is everybody makes mistakes sometimes. If you see a flaw in the calculation, you can't correct me. But the TAs are supposed to be going through and rigorously checking all the calculations that are done, because we don't have that same normal feedback loop than we might. And you could say, why haven't you perfected it? This is your 6th year teaching it. But every year the code has tweaks and changes, and this year they're implementing an actually very large change. So all of the math and all of the example questions that I had done in the past is now obsolete, and I have to redo every single math question that we submit that I'm going to be providing you with. Almost every, so probably 80-85% of them. So here are just a few kind of projects that I've worked on in the past. When I worked with Blackwell, I was really fortunate to work with some of the coolest, funnest architects around. This is the Canadian Peace Bridge Customs Plaza. Pre-COVID, if you ever drove back across the border kind of through the Niagara region, you might have had your car torn apart underneath this beautiful structure. At the time, it was supposed to evoke a sense of an upside-down canoe. At the time, I was doing the work on this in 2004 and 2005. The ability for 3-dimensional technology, whether it was just basic drafting or even modeling software was pretty obsolete. So there was a lot of rigor and kind of double checking of everything in this system, and hacking software that could do 3D stuff but was not meant for things of this kind of curvature and complex geometry. One of the things I do is kind of tour the country sometimes talking about complex geometry and engineering and how to produce drawings for complex geometry. So it's something I'm kind of passionate about. This is a really cool project. The Native Child and Family Services headquarters, which was cool in and of itself. And then this building is a small structure within it. And this is kind of a modern day longhouse. They have smoke ceremonies in here. They do a lot of kind of indigenous appreciation inside this. What was really cool about this is the architects said, listen, we want to build a longhouse. Obviously, structure is integral to this design. Can you draw some stuff? Tell us what you think. We're going to go work on this stuff over here, and then we'll meet up later. So my partner, my husband at the time, or my husband now, who was my boss at the time, we kind of sat down and worked on this and developed this reciprocal frame plan and created a 3D drawing of it and gave it to the architect, and they were like, we love it. And they just took that drawing and sent it off to the contractor to build. So nothing else was produced except that 3D CAD file, and off it went. So there are unique ways of doing contract document layouts. The main building itself was a concrete building, 4-story concrete building, existing building that they wanted to cut this opening in here in all the floors. So obviously we're cutting the concrete and all the reinforcing steel that's in it. You can imagine these little things here are the columns. This is right in the middle of it. If you've ever kind of held up a bed sheet at the 4 corners before it's on the bed, you know that where it wants to sag is in the middle. So these middle points, right where we cut the hole, is where we were kind of cutting it out. So it wasn't too bad. That took some work and calculations, but it wasn't horrible. On the roof, they were adding up to 8 feet of soil in spots. Now, if it's not obvious, soil is ridiculously heavy. Putting it up on the roof of a structure takes a lot of engineering. This was an existing building that was never designed to see those sorts of loads. So it was easy enough to design a structure that could take the loads underneath it. We couldn't even reinforce the existing concrete structure. It kind of became a cyclical thing. As we added more concrete to deal with the load, the self-weight of the concrete overloaded the parts at the bottom, including the soil on top. So we needed a system that could essentially unload the roof for the new load we were putting on. So what we did is we put this filigree of steel members underneath the concrete structure, about this far underneath. And then periodically, where you can see these little dots right here, we put hydraulic jacks in between. And then we would jack up the hydraulic jacks that would push the steel down and lift the concrete up. So the steel was taking the load and unloading the concrete. And then the steel, we could tell how much load it had on it by how much it would deflect. So we were able to design the system, but also give them a calibration technique for that preloading in the roof. It was such a cool structure. When you went in there, the beautiful steel is this fine web of steel underneath the concrete. It was gorgeous, but they had to fireproof it. So it all got covered up and no one's ever seen it except for the few times we got to go in and inspect it, which is a bit of a heartbreak. I've got to work on a lot of really cool houses. One of the great architects that I've gotten to work with is Drew Mandel. These are 2 of the projects he's done. This one's really cool. This cantilevers out over the pool that you can see down here, and it looks like it just disappears. Like doesn't look like there's any opportunity for the back of that truss to kind of cantilever out. So we took the side system and had to switch it around and transfer it to the top and bottom. So a really kind of feat of engineering for what looks like, yes, a fancy house, but still just a house. This is a canopy for the Sisters of St. Joseph building. near the Don Valley or along the Don Valley. The canopy cantilevers out quite far. What you can't see is there is webs of steel on top of this that taper down. It's showing me backwards, so I'm getting myself confused. It tapers down to a point, so that you can't see the steel as it comes out to the edge. So it gives this illusion of it being just a very thin steel plate. You can see it from above, so it did have to be kind of architecturally processed, and it was Shim Sutcliffe, who are meticulous in their design. Every screw placement is drawn and thought about in great detail in the work that they do. If you don't know who they are, look them up. One of the top award winners of the Governor General Awards in Canada, kind of combined with Pat-Cow Architects. This is the Verdant Walk by North Design Studio, whose two partners both teach here at U of T as well. This was a cool little structure, again, back before we had really good 3D modeling techniques. This was like, I want to say 2007. So just kind of, I wanted to show it because it's other profs that work here. Really cool little project. It's toured around North America. It started out in Cleveland in the mall, which is not a place you go to shop. It's the big grassy strips where they kind of parks, what we would call a park, I guess. I'm not sure where it is now. I know it ended up in Montreal for a while, but I'm not sure where it is now. Again, getting into more complex 3D geometry. This is the Lasalle School for Engineering, where I didn't do the base building, but I did do the facade support. So what was interesting about this is the facade was out 1/2 meter from the edge of the concrete slab. So if you're trying to hang something out off the edge of something, it wants to drop down. So we needed some way to pick that up. The facade people said, not a problem, we can stack out Z-girts and make that happen, but the windows were really difficult. So we needed something that could support the windows. The facade couldn't support the windows needed their own support. The difficulty is that every surface was curved, so every piece of glass needed to be on a curve, and it was faceted into pieces, but then those facets weren't in the same plane relative to each other even. So they were faceted within that as well. If you want, take a second and Google the Lasalle School or the York School of Engineering, Lasalle Building of Engineering, and you'll see what I mean. It's also called the Cloud. They hired a mathematician to pattern the triangles that this building was fabricated out of, who also actually happens to teach in the engineering and mathematics and physics departments at U of T. And I think every now and then he might even do an elective in the architecture department. So it's he was one of the first crossovers between mathematicians and engineering, which is kind of a field that's really grown lately. And then so all of this needed to be figured out, but the glass doesn't actually connect right here. It's in 25 millimeters from that and still out 50 millimeters more from that. So kind of figuring out where all these things were in three-dimensional space when you had no relative planes with each other kind of took a taxing amount of work. The very first, they also had the added difficulty that normally in a building, you build the concrete structure, you measure everything for as-built site conditions, you go back, you fabricate the steel frames. You come back, insert the steel frames, measure everything for the as-built conditions, and then go back and fabricate your glass. This was on such a tight timeline that they needed to be building the concrete structure while they were fabricating the steel, while they were fabricating the glass, which meant everybody had to know everybody else's work was absolutely perfect. And nobody was really willing to take it on, and I guess I was crazy enough to say yes. But that also meant we had a compressed timeline. So I had 6 weeks to do 137 frames. The first frame took me 3 weeks because I had to figure out all the problems. As you can imagine, I was panicking a little bit at the end of that 3 weeks. But the second frame took me 3 days, and then the third frame took me 3 hours, and then I got down to about 30 minutes a frame. So it was a lot of work and very little sleep, but I was able to meet the deadline within that. What is always kind of really fun and interesting, and if you ever have a chance to attend my complex geometry lectures, we did get a call from the site about actually happened to be, no, this frame over here. They called and they said, there's a big problem. We've installed it. They're not flush with each other. There's a problem here. Things are not going to line up. And you can see that right here, those look like they don't line up. So I said, okay, well, I'm about to go. I have somewhere I have to go. Can it wait? And they were like, no, you have to come right now. I said, okay. So I stopped by at the site and went and took a look at it and saw the problem immediately. The problem was that this right here didn't matter. That was all going to be channeled out and have drywall cover it and was kind of irrelevant. The only thing that mattered, if you come to look at this picture right here, is what happens where the window plane is, so out along these edges. And you can see this particular one crossed two frames. The only thing that mattered, imagine if there was a break right here, is if that point and that point were in line with each other. So we took out a ruler, we held it out there, and we could see that it was fine. And I didn't get a single other call from the site for that project for all 137 panels. So I said, all right, are we all done here? Can I go? Because my wedding dress is in the car and I'm on my way to the airport to go get married. And so luckily they did not have to bother me again because I was in the Yukon getting married later that day. And so I mentioned Pat Cow Architects being one of the other big winners of the Governor General Awards. This was a project that McLennan Yonkons Miller, or MJMA, did in partnership with Pat Cow that I was lucky enough to get to work on. This is still one of my favorite projects of all time. It is a building that spans 54 meters, so it looks like it touches down right here, but it does not. The column supports are here and here. This is just where lateral load can come out into a concrete floor. The reason it can't touch down here is this is a slab. There's nothing underneath it. Underneath it is a field house, or basketball, volleyball court, for those that don't know what a field house is, which is larger than this footprint right here. So we couldn't actually touch down the steel trusses right there. This is just one of the trusses. The interior trusses are only 1 story deep, so from here to here. And the rest of the building is hung from the underside of those trusses. So we have basically a very long bridge acting as a building, supporting floors below. So a really unique structure in so many ways. So let's talk about the course for a few minutes. Let's talk about the marking first. You're going to have your mark broken up into 3 parts. The first part is assignments. So the assignments are going to be available on Quercus the day of each class. Now, there's no set time. You can watch these whenever you want, but the idea is that all lectures will be posted on Wednesday. So Wednesday, the assignments will be available for you to complete. There is no time limit on the assignment once you open it, but it does have to be submitted by the next Tuesday at midnight. And if you don't submit it, it'll automatically submit it. So there's no time limit. You can take your time, work through the problems. The answers will be available the day after it's due. So if you submit it on Friday, you'll have to wait until the next Wednesday to get the answers. The answers will be available on Quercus. And sometimes they'll have little notes or summaries about why that's the right answer, or a bit of an explanation with them. So take the time and go through those, write it out on a piece of paper, because when you do the exam, you'll probably have a hard time going back and pulling all that information. What we used to do is have a tutorial where the students would go to the tutorial and the TAs would go through the assignment on the board. Obviously, we can't utilize that format now. So one of the TA's jobs is you will submit all of your questions to the TAs. The TAs will take the first round at possibly answering them, or at least compiling a list of questions. If they think a question's a really good question that the rest of the class deserves to hear the answer to, they will formulate a list, because maybe if you asked it, 5 other people asked it as well. They will compile a comprehensive list of questions, and then I will review that list and either answer the questions in the announcements section or a page within the lecture module for you guys, or I will record a whole new video. If it's something that seems worthy of it, I will record a whole new video kind of addressing those questions with the answers. All the assignments are going to have equal weight in the final weighting of the assignments. You're going to see that they have different values in Quercus. Don't worry about that. At the end of the term, I download them all and make sure they have the same proportional value towards your term. If you cannot meet the assignment due date, you have to let us know. It is totally reasonable to be sick. That happens. I get it. One of the advantages is that you don't have to go to class. So there is a little bit of help in that respect. But you have to let us know if you can't meet the due date. I have to make changes on Quercus to make that happen. So you have to let me know ahead of the due date, okay? The project. So the project has two parts, part 1 and part 2. It's due the last day of the semester. I think it's like the 22nd or the 23rd this year. It's in the syllabus or the course outline. I have been asked to make that the due date by the director. You are more than welcome to upload your projects to the FTP site before that date. I will set up the FTP site with the assigned folders, but also the project outline, which will come later in the term, will show you how you should name your files. I am obsessive about how the files need to be named, mostly because it helps me keep the marks organized. I can tell at a glance, I can go through and mark them in order very easily if you follow the format I lay out. Part 1 used to be done in partners, but I think we're gonna have to kind of go through and do it solo. That might change. Maybe I'll send out a survey and see how people feel about that, because you can still communicate over the internet. You don't have to meet face to face. You can Zoom with each other or something like that. Right now I have it set as individual, but I'm happy to talk about that going forward. But the idea is that you're going to draw a static object. Now we're going to talk about this later in the term, but static means it doesn't move. So a bike rolling down the street does not meet the criteria of the project. And as much as I say this every year, somebody inevitably does a bike, which drives me bonkers. And you're going to draw the free body diagram, something we're going to talk about this term. You're going to explain all the loads on it and what resists all the loads and why it is stable and static. Part 2 is you're going to do some hand calculations on some assigned members. So I've created a fake building that I will assign everybody some members from, and it's randomized so that the difficulty level is pretty consistent across the board. And you will be told exactly what that means later in the term about how you design these, or the hand calculations are going to go, but it's stuff we're going to learn throughout the term. I recommend doing part 2 before the exam. People who do not do part 2 before the exam, or at least read it and get your head around it, do really bad on some of the questions in the exam. The people who do part 2, or at least take a look at it before the exam, ace those exam questions because they're very similar. They have to be. It is the point of the entire course. We have one ultimate goal at the end of the 2 courses, and those questions are it. So the project has some of it and the exam has some of it. Again, you've got to let me know ahead of time if you can't meet the due date. The exam. The exam will be done on Quercus as well. So online, you will have a set time for it. If you if you're meeting with student services for extra time or special requirements for the exam, let them know as early as possible so they can contact me, because I have to make modifications in Quercus for that to happen. So and if you could, let me know even as well, so that I kind of have it flagged as a radar for me that I'm going to have to make those changes. Because it takes a little bit of time. I have to kind of go in and fiddle with the program to make it work. Quercus was never meant for kind of this level of complexity of stuff happening through it. They're adapting and they're making it better, but as I saw in March, no one else had done it at the time. So I was really the only one that had done it at U of T, or at least in our department, for that level of exam, that they've kind of used me as a resource for the summer courses as well. Because it's on Quarkus, there's a variety of types of questions. There's multiple choice, fill in the blank. There's definitely going to be math and or table matching questions. What's really interesting about Quarkus is I can set it up so that it has different number values. So the same question, different numbers. The idea is to kind of try to limit the ability to cheat. Not that I think you guys would do that. You guys are all wonderful. I know you're not going to do that to me. But the department has mandated that we try to at least utilize the tools that are available to us to limit that possibility. We want to make it harder to cheat than it is to just do the question yourself. I might also have question pools, so everyone might not have all the same questions, but I do group the questions. So question 4 might have 5 different versions of it that are all the same difficulty level, and it will get randomized out around the course. So don't worry, you're not going to get stuck with all the hard questions while someone else in the class is going to get all the easy questions. I don't set up the randomization that way. Like I said, obviously it's going to be open book. I'm going to hope you're not texting with each other and kind of sharing answers. Like I said, that's why some of the randomization is built into that. What I do prior to the exam is I provide you the appendix that I would have put at the end of the paper copy were you writing it in person. And I always gave that appendix even before we wrote the paper copies of exams so that people had an idea of what they didn't need to print off and kind of have ready beside them. Because there are a lot of downloads that I send you or give you through Quarkus throughout this course. And some of them are 60 pages long, and I've written the exam to only use 3 of them. So I extract those 3 pages and those 3 pages only and provide them within the appendix. Inevitably, somebody's going to ask me, do I need those other pages? Obviously not, or else I would have included them in the appendix. So if it's part of the exam, and it's from those lists, and it will be available to you ahead of time so you'll know, those would be the only pages from that list you might need. Assignments, you might want to find a way to write out the assignments or print out the assignments so you have them handy for when you're doing the exam. Questions or lists and equations from the lecture notes. I love those in exam questions. So I recommend having a little notebook beside you that you write out lists and you write out mathematical equations that you can have kind of sitting there in the exam that you can just flip through. So you're not trying to go through, 40 slides per 12 lectures, trying to find the one you need. You've got a little handy book that has probably 90% of the information you need for the exam. Classes. So the PowerPoint will be posted to Quarkus, and I will provide links to the videos to Quarkus. The first slide every week will often have the learning points that we're going to talk about throughout the lecture. The last slide will list the important items that we've talked about. The way I make that list is there's obviously the stuff that I have to test you on, that you need to know to study for and pass the exam. There's also some stuff that's just really hard to test on, but I think as an architect is just so valuable that you know. So I'll break the list out into 2 parts, the just useful tips for architecture life and studying for the exam part of it. PowerPoint and video links will be posted the Wednesday of each week. By Wednesday of each week. Sometimes it might be Tuesday or Monday or even a week ahead of time. I want to try to stay 2 weeks ahead of everything. I'm already behind that because I'm only a week ahead right now. But if it doesn't show up until Wednesday morning, don't stress out. It'll be there by Wednesday morning. Assignment answers, like I said, will be available after the due date. Submit any questions to the TA, and then I will either post or do a video link for the answers to the question. There are 70 of you and only one a little old me. I also have 185 students in my undergrad class and up to 25 in my graduate class. I also have my 2-year-old and 4-year-old home doing homeschooling this term. Just try not to make me cry too much, please. But I want to be available for you guys. I want to do whatever I can. And remember to provide the class number. If you do have to send me an email, if the TA couldn't help you, make sure you include what class it is. Otherwise, I will have no means of knowing what you're talking about because all 3 courses are structural engineering based, and I might get myself confused. So what's my job? My job is to meet the requirements set out for the class lesson plan. That's pretty obvious, I would think. Number 2 is meet the needs of the majority of the class. This one always sounds kind of like a jerk thing, but you can imagine in any class there are the people that find it pretty easy. So those might be the advanced set. Maybe you have an engineering degree or you did a physics degree as your undergrad class. You might find these courses easy. That's fine. Come along for the ride. If you could help out your peers, that would be wonderful. If you're a person who struggles with math, I would recommend right now that you try to familiarize yourself with some of the math issues, or look into finding yourself a tutor. Maybe you could reach out to one of those students that is more advanced in the class. But there will be math, but the majority of the class is going to be in that middle section, and the course has to be geared towards the majority of the class getting the most they can out of it. And then my 3rd requirement is to be reasonably available, but reasonably available to everybody equally. And there are a lot of students this year. So that doesn't mean you get an hour of my time every week. Probably throughout the term, you can ask a couple questions of me directly. Make use of the TAs though. That's what they're there for. Send your questions, and then the TAs will compile a great list of questions for me that I will make sure everybody gets these great questions answered. So that isn't to say don't bother me. It's let's follow the proper order of asking the question before you make it to me. Your job, obviously watch all the videos and review all the PowerPoint lectures. You should try to do all the examples, download all the materials, submit any questions to the TAs, do your assignments, complete the project, and study for the exam. It's not too hard. You got it. This is no problem at all. You should take notes. Like I said, having a little book kind of sitting beside you. The advantage here is you can pause me to write things out as you want. Calculations, lists, and equations are wonderful for exams. I've already mentioned it. I want you guys to pass as much as possible, so listen for my cues. If something's a great exam question, I'm gonna tell you it's a great exam question. I'll put flashing banners around it. I will go, great exam question, here you go. I want you guys to do good on this, because it's a hell of a lot of paperwork for me if you fail. I have to answer all these ridiculous questions and submit forms, and you're gonna get mad at me. I just don't want to have to deal with that. So let's just make sure everybody passes. I have to make it at the appropriate level of difficulty, but you do what you can to make yourself pass, and I will do what I can to make sure you pass as well. One of the most popular questions I get is, why is there no textbook? I would love for there to be a textbook for this class. Unfortunately, there isn't one right now. We touch on information from so many different books. We talk about statics, which there is a book for, there is a textbook for. Unfortunately, it's an American textbook that follows different codes. There is a structural analysis textbook, which we're going to cover structural analysis. Again, it's American and follows different codes. Then we actually end up using our codes as well. We need the National Building Code of Canada and the Ontario Building Code that we reference. And then we have the material handbooks that we need to look at for wood and steel and concrete. All of those add up to a hefty price, and for each one we only need 10 to 15 pages anyway. So for the first 2 books, I create all the examples following our code. And then for the last 5 books, I extract the information you need from those codes to make sure you have it. They're all available in the library. Go check them out, take a look at them. Maybe you can find them online. Maybe you want to buy them yourself. They're going to come in handy down the road, especially the National Building Code of Canada and the Ontario Building Code. You're going to wish you had those at some point. But they change every few years, so it can be really expensive to kind of update that library as you need to. In fact, this year, a few years ago, the National Building Code issued a new version that has new requirements in it. But it's not legal in Ontario until the Ontario Building Code adopts the NBCC. This year, the Ontario Building Code finally adopted the 2015 NBCC, which it kind of triggers all of these new clauses that we didn't have to follow up until now. And so now all of my, like I said, all of my calculations all have to be reworked and redone. So I'm going to try to be super diligent about doing that, but it's a big, they kind of told us that this was happening in May, and it's happening now. So on top of everything else, all of my coursework kind of has to be reworked to kind of give you the latest and greatest information. Online resources. If you see a word or a topic that you're still struggling with, Google it. You're going to find lots of other resources. Maybe somebody talks about it in a way that you like better. Doesn't invalidate what I'm saying, but there are different voices for things. I'm also currently doing my master's in lightweight fabric structures at Lasalle in Germany, which is basically the Bauhaus campus. And you don't get to be exempt from it. So every couple terms I fly to Germany and do 2 weeks of intensive courses. It was interesting because I don't get exempt from the structural curriculum or the architectural curriculum. And in the structures course, they were showing videos that I have always shown in my classes. So it's interesting to see that the structures curriculum is basically the same across the world. People just might term things slightly differently, present it slightly differently, but the actual knowledge behind it has had very little advancement in 50 to 100 years. Some things even longer, that we're going back 150 years, that we're doing the exact same we did 150 years ago. One good example that some people find handy, and I know like even senior architects go back and watch this video sometimes, it's Structures 1 and Structures 2 combined into kind of one video. They do the format slightly different, but all of the information is there as well, and using the exact same techniques I use when I teach my course, and I had never seen this before I started teaching this course. So one of the questions you might ask is, why are we even here? Why are we doing this class? We're going to hire an engineer. I don't need to sit and listen to structural engineering. Well, you guys make a lot of the preliminary choices long before you've ever talked to an engineer. You've often picked what material you want to use. You've often picked the layout of the building. And you've probably even done some preliminary sizes. And so the material often comes with what you're talking about with the client and is tied to the layout. The layout is usually prescribed pretty strongly by the client and yourself, but you have to know what's reasonable within the materiality choices. And preliminary sizes are very important, still again, long before you've talked to an engineer. You might not hire an engineer. Well, we'll talk later about the phases of construction, but you probably haven't talked to the engineer when you're making those preliminary sizes, and it's really important because the preliminary size is usually how deep a member is, or like how deep your ceiling needs to be to hide your beams in it. If you have a 10-story, or if you have an upper bound on the maximum height of the building, and you want to fit in 10 stories in that, but you haven't thought about, but you only draw your ceiling depth to be this big, and your beams need to be this big, you're not going to have enough room to fit your building in. All of your ceilings need to drop, which means you could end up losing an entire floor of your building. And if that's, for example, commercial space, your client has just lost an entire floor of revenue for their building. So it can have really big impacts on the early choices you're making before you've even talked to an engineer. And I'm going to give you the tools to do those preliminary sizes. Again, it's not the final engineering, and we're going to learn how to do the final engineering as well. But it's really important that you know preliminary sizes separate from engineering. And it's important that you know both, and it's important that you know that they're two distinct topics, that they're not the same thing. You also need to know what the limits of those materials are. If you have a floor plan that has your columns at 12 meters by 12 meters, you've got to know that concrete is probably not the right choice for that building. But if you had 6 meters by 6 meters, the concrete might be a beautiful choice for your building. So understanding the materiality limits is really important. You also need to understand that sometimes a small change can have a really big impact on the design, and that some of those things are very tightly tied together, like depth and length or strength and deflection. For example, making something longer isn't a linear relationship to how deep or how big your ceiling needs to be for that element. It's a non-linear equation, so you don't just proportion it up. So these are difficult concepts, and sometimes there's difficult math with it. You're going to need to do the math a few times. I like you to kind of write it out while we're doing the examples. You're going to have assignments to work through it. You're going to have the project to work through it. And all of that should prepare you for the exam. Ultimately, for the math questions, I try to ensure that throughout the lectures and throughout the assignment that you have a minimum of 3 examples for each type of problem that we're going to do. They might not always look the same, but I can tell you that they will lead you to that information. If that's not enough for you, and I get it that some people that's not enough, but for the majority of the course, that is more than adequate amount of examples. And each year we kind of get a few more, but we're in a weird place this year that I have to rework all the examples and assignment questions. Feel free to try to hunt more out on the internet. You might find some that are following the American code. So just try to understand what things are not the same about those questions. We're spreading our learning knowledge over 2 terms. We have Structures 1 in the fall and Structures 2 in the winter term. In Structures 1, we're going to learn how to create the system. We're going to learn the preliminary design. So what should I be drawing in those drawings to show my ceiling depth, and how big should my columns be in that drawing before I've even hired an engineer. We're going to talk about loads and load paths and element loading. So what type of loads go on systems. But we're not going to get any answers. That's just going to be all the things happening to the building. Structures 2 is going to be how we resist all those loads. So we're going to design and size the members, which sounds pretty easy, except it's where all the concepts come together, and every material has a different method of doing that. So we're going to talk a lot about the materials in Structures 2 in the winter term. So I'm going to stop this video now. There's a unique thing that throughout the entire course, the only time ARC2044 and the undergraduate ARC281 are the same is the lecture on strength, stiffness, and stability. So I'm going to stop this and go create that lecture now, and both classes are going to get that one same video. And I will probably end up breaking videos into smaller segments just to make it kind of a little more user-friendly. Maybe in between topics is a good place to pause things. So we just completed the intro to the course, and now we're going to move on to our next lecture. So I'll see you in our strength, stiffness, and stability lecture.